Banked angles. This is going to be where instead of the car going on a flat surface, the car is going to go on a surface that it's at an angle. So what I'm going to do, I'll tell you what, I'll race you. Let's draw ourselves an inclined plane. There. I think I won. This weird little thing here is supposed to be a car, but I forgot to draw the tires. Oh well. What we want to do is draw out the information we know. I know that's FG. I know that's Fy. I know this is Fx. I also know that that is Fn. Okay, we usually don't use this Fn too much, but this is what we're going to do this time. We're actually going to draw a dotted line out of the center of the vehicle, and I'm going to stop it so that I create a right angled triangle with this Fn, which is the same as this Fy, but this thing is going to actually be the hypotenuse of this new triangle I created. So this is going to be my 90-degree point. So this triangle and this one are not the same because this is a component here. This is the actual hypotenuse. So what I want to do is I want to find out what this is, and I want to find out what that is. This one, whatever it is, I'm going to slide it down to here. It's going to face that way. And so since this is theta and that's theta, this is theta. And opposite of theta, that's going to be Fn sine theta. And this one here is going to be Fn cosine of theta. So I've just created things, and the reason why I'm using this as opposed to my Fx, which comes down this way, is that my circular motion goes towards the center of a circle regardless of if you're banked or not. So this is always going to be this way, even if the surface is flat or if it's banked. So no matter where I make my banking, I have to have this vector going towards the center of the circle. And so what I'm going to do is I'm going to be able to use all this information to figure out what angle I have to tip this all at so that the car does not slide. So let's write that down. And we're going to look for the theta needed so the car won't slide. And of course the surface is frictionless. That makes it all even harder. No friction. If we added friction to this, well then you could say that well, you give it a force of friction and then you would have a force of friction going backwards here. But let's just continue with this. It's frictionless. So my Fn sine theta then is going to end up being equal to, actually I'll do a sum of forces. So here's my first little step here. I'm going to go, well, the sum of my forces is going to end up equaling Fn sine theta, which is going to have to add to centripetal force, which is in the opposite direction, and because it's not moving, we don't want this thing to slide up or down, so it's in equilibrium, so it equals 0. Really what that means is I'm saying Fn sine theta is going to be equal to Fc, and one more step, Fn sine theta is going to be equal to mv squared over r. This is fairly important because we're going to be using it a little later on. Second point I'm going to make, if the car is not supposed to slide up or down, then we can actually say then that my Fn cos theta, this one here, Fn cos theta, is going to be equal to Fg. These things aren't going to slide. So, and I guess I will. Sum of my force, Fn cosine theta plus minus Fg equals 0. So that means that Fn cosine of theta is equal to Fg, which means Fn cosine of theta is equal to mass times gravity. And that, actually, you know, I'm going to take this one step further. No, I won't. This is also fairly important. So now I have Fn sine theta, I have Fn cosine of theta. What I want to do is I want to solve this one here for Fn. So Fn ends up equaling mg over the cosine of theta. Now I want to take this Fn, I'm going to put it here. So So I'm going to get mg over cosine of theta multiplied by sine of theta equals mv squared over r. Now I'm going to cancel my m's, and I'm going to get sine of theta over cosine of theta. I have a g on top. I'm going to bring it to the bottom. So that's going to equal v squared over rg. And sine over cosine is tangent to theta. That's v squared over rg. There. That is the formula to use to figure out what kind of a theta is needed so that you're going to drive around a banked curve without sliding. So, at what angle does it need to be banked? So let's see. Why don't we do a quick one here? I'm out of space here, but I'll just grab a new piece. Let's say, first of all, let's rewrite our formula. Tangent to theta is equal to v squared over rg. We want to know what theta value you need. So what angle will you need if you know that your curve has got to be 50 meters. That's all the space you have. And most cars will be exiting onto that radius curve at about 50 kilometers an hour. So you're leaving the perimeter, you're going onto one of those clover leaves. We want to know what angle we're going to bank it at so that in a frictionless situation the cars aren't going to slide off the road anyways. So basically in winter, how much do we need to tip that road so at 50 kilometers an hour the cars don't slide off? Okay, so you're coming off the road, we want to know what this angle is here so that this car doesn't go this way or that way. You want them to bounce off. So no motion, no motion. Okay, we want to stay perfect. So let's find this theta. So let's see here. First of all, we need to convert that to meters per second. I remember from before that it's 14 point something or other. No, I don't remember from before. So 50 divided by 3.6, 14.14. So 14 meters per second. That's what that is. Tangent of theta equals v squared over rg. Let's fill that in. Tangent of theta, my v squared, 14 squared. My radius is 50. I'm lazy, so gravity is 10. Tangent of theta, 14 squared divided by 500. 0.392, and if everything works out right, I should get an angle when I second function tangent. My answer, 21.4 degrees. There you go. Even in the middle of winter, you still have a little bit of friction on your surface of your road, so if you tip your road up at 21.4 degrees, and then you also include friction, you're going to be able to go a little quicker than 50 kilometers an hour and not slide. But there you go, banked angles.